Okay, hello, welcome back. This is the last session for today. We have two speakers. The first one is called Frey Drehamar, and he's gonna talk about his just-in-time compiler for Erlang. Thank you a lot.
Thank you. Do you hear me? Okay, good. The title of my talk is Beamjit. It's about an LLVM-based JIT compiler for the language Erlang. But before I start with that, I probably should tell you about who I am. I'm a researcher at the Swedish Institute of Computer Science, mostly known for our Prolog system, Sixtus, but this talk is completely Prolog free. At Six, I work on programming languages, programming tools, and also distributed systems. And this project I described today, it's a project funded by Ericsson, who develops Erlang, and it's joint work with Lars Rasmussen, who also works at Six. Well, enough about the preliminaries. This talk is about the automatic synthesization of a JIT compiling virtual machine for Erlang, and also our experiences with LLVM and in particular MCJIT. And some of my opinions are a bit negative, but I don't say that to antagonize you, but rather to solicit feedback, and hopefully you will tell me that it's hard because you're doing it wrong.
If you didn't have negative experiences, we'd be surprised.
Yeah, that too, probably. My talk is structured as follows. I start with a quick background into just-in-time compilation in Erlang, in the Erlang virtual machine, which is called Beam, and the goals of our JIT implementation. Then I go into a deeper level of detail where I go through the different steps we use inside our JIT-based VM. And then at the end, I talk about some of the strengths and weaknesses we've seen with LLVM. Okay. Just-in-time compilation is a fairly common optimization technique for improving the performance of virtual machine-based languages. As you can see, almost all cool languages have at least one implementation of a JIT. So for example, for Python, this is Psycho and PyPy. Smalltalk has Cog. Java, Hotspot, and that is more or less the standard way of running Java today. JavaScript, Squirrelfish, Extreme, SpiderMonkey, and since I wrote this slide, there is probably a number of new.
V8, which predates Squirrelfish.
Yeah. So everyone is writing a JIT today. And at an LLVM meetup, I can't assume that everyone knows about Erlang. So Erlang is a functional language developed by Ericsson in the late 80s, early 90s. It's soft real-time. It was created to control telephone switches. It's multi-threaded with share-nothing semantics. That means that the only mechanism threads have to communicate with each other is through message passing. And that combined with powerful supervision primitives allows you to do or program very fault-tolerant systems. And that combined with facilities for hot code loading and hot code upgrading means that you can write really, really dependable software, that stuff that never fails, and if it fails, you can patch it without anyone even noticing. And all these basic functionalities wrapped up into a large framework which is called OTP, well, which is abbreviation of Open Telecom Platform, which is just nonsense, but its name. Erlang is, as I said, it's a virtual machine-based language. We compile it down to a virtual machine that is called Beam. And the Beam machine is a register machine. Its instruction set consists of around 150 instructions, which are at load time specialized into around 450 different macro instructions. And you do that at load time where the loader has an integrated p-pole optimizer. The instructions are very CISC-like. For example, you have the add instruction handles both small ints, big ints, and floating point values. So it's the same add instruction for all these three data types. The interpreter, or the virtual machine interpreter, is in handwritten C, mostly. There are some parts that are automatically generated. And a nasty thing with this implementation is that there is no authoritative description of the semantics of the virtual machine apart from the C implementation, which complicates things if you're planning to make a JIT. Erlang also has, since I think around 10 years ago, an ahead of time compiler which compiles Erlang to native code. And traditionally, it has supported x86, PowerPC, Spark, and ARM using homebrewed code-generating backends. But currently, they are working on an LLVM-based backend, which is called Erl LVM. And if you read the LLVM weekly news, you saw that they got some stuff committed 2 or 3 weeks ago. And that is all I'm going to say about Hype today, because this project is completely unrelated to that path. And why, when we have a ahead of time compiler, would we want a JIT compiler also? Well, a JIT has a number of benefits. Mainly it's because it increases flexibility. A compiled Beam module without native code is completely platform independent, and it's not coupled to a particular release of your virtual machine. So it becomes much more flexible. Also, the JIT can do something that the Hype cannot do, namely cross-module optimization. And a JIT integrates much more easily with hot code update and things like that. When we started the project, we set up a number of goals. The first one, as I'm lazy, is to do as little manual work as possible. We wanted to preserve the semantics of the plain unmodified Beam. We also wanted our JIT to stay in synchronization with the plain Beam. If, for example, you find a bug which you fix in the reference implementation, the JIT should automatically adapt, and you shouldn't have to patch it. And we also wanted a native code generator, which is state of the art. And how do we plan to make this work then? Well, the only specification of the virtual machine we have is the C code. So we are going to use the C code. We want to parse and extract the semantics of the instructions from the C code. And then we want to use that to extract C code and other forms of code which we will need for our just-in-time compiler. That's the background, so let's go into details. And just-in-time compilation, as it applies to Beam, consists of, I'd say, 3 main steps. The first one is profiling. We want to cheaply find out which parts of the code would be suitable for native code compilation. When we have found something that looks good, then we want to do tracing to figure out exactly what we should compile to native code. And then finally, when we have a good trace, we want to turn it into native code and then generate the native code through LLVM. Yes. So just-in-time compilation as it applies to Beam, we want to use a lightweight profiling to detect where we are at places in the code which is frequently executed. And when we found such a hotspot, we want to trace the flow of execution until we get back to the same point, meaning that then we probably have found a loop. And probably a loop which we spend a lot of time in will probably make sense and be good to turn into native code. And here is the first unique thing about Beamjit, our JIT. Namely that instead of, as for example in Java, you trace the execution of your Java program, we trace the execution of our interpreter. And the reason for that is, as I said before, instructions are pretty CISCI. So we have in a single instruction, in fairly simple instruction, as for example an add, we have a bunch of execution paths, one dealing with floats and float plus a float, and the other one float plus a small int, and so on. So doing it this way allows us to actually specialize our native code for the particular case which is in the trace we have decided to natively compile. To do this, what do we need to do then? Well, we need to support 3 basic execution modes. One is profiling, one is tracing, and one is running code in native code. And of course, our interpreter has to be modified to support mode switching between these 3 modes, meaning that we have to turn on, turn off tracing, we have to pass state from the interpreter to the native code, and when the native code is done, we have to pass that state back into the interpreter. And we have to have some way to come up with native code. And for that, we need the semantics of the instruction. So if we take them in order and start with profiling. Already said that profiling is the first step we do in figuring out what we should JIT compile. We do that by having the Erlang compiler insert special profile instruction at locations which can be at the head of a loop. And for each such location, we maintain a timestamp and a counter. And we measure execution intensity by increasing that counter if we had visited that location recently. Otherwise, we reset it. And if that counter goes over a threshold, we start tracing. It sounds simple, but it looks like it works. We also blacklist location which never produce a successful trace, and also when we have gone all the way to native code and when we execute it and we find that we never execute a complete loop in it, then probably we selected the wrong thing, so then we blacklist it throw away the native code, and then we let that blacklist slowly decay, because in a running system, it's not unheard of that the execution pattern will change over time. So we're not blacklisting things forever. As I said, when we found something that's executed frequently, we start tracing. Tracing requires that we record the basic blocks we execute, and to do that, we need to figure out which basic blocks are we executing. And that we do by analyzing the source code to the interpreter. And for that, we use libclang and the C bindings to the Clang frontend. And we use, as this is an Erlang VM, we have written a small binding from libclang to Erlang, because who in their right mind would write a compiler-like tool in a language which doesn't support pattern matching? Should I have said that, or should I watch my back the rest of the evening? And we use this to flatten the variable scope, so we push all variables up to the top level. We remove all nicely structured C loops, replace them by ifs and gotos. We make all fall-throughs explicit. So in short, we turn nicely structured C into a spaghetti of basic blocks. More or less, we get the control flow graph. And for future use, we do liveness analysis of these variables. And what you see down there is just part of the CFG. It's perhaps 1/10 or so of the CFG of the emulator. When we now have the CFG, it's not very hard to implement tracing. We just generate a new version of our interpreter from the CFG. And for each opcode, we generate a tracing version and a non-tracing version. And for each basic block we pass through in the tracing version, we record the basic block identity and the program counter into a trace structure. If the trace becomes too long, we abort tracing and switch back to interpreting mode. If we reach the profile instruction we started the trace from, we have found a loop, and then we can go on to the next step. Worth mentioning is that to switch between interpreter modes, we use a trick. The Beam, the reference implementation of Beam, is directly threaded, and directly threaded means that in the loaded code, an opcode is represented by a pointer to the code implemented that opcode. But now when we have to switch between two different implementations, we convert it to use indirect threading. So instead of having a pointer in the code, we have an index into a table from which we find the opcode implementation. Of course, this costs us around 10% in the performance degradation, but it makes it really easy to switch between execution modes. The nasty thing about this is that the compiler cannot assume anything about the control flow, because the code can more or less jump from one basic block to each other basic block. So that costs us a lot of performance. So to work around that, we have refined our implementation. So we modify this basic interpreter loop as little as possible, and then instead we create a completely separate trace interpreter. So we switch around from one interpreter to another when we go from profiling to tracing, and we limit ourselves to jumping back into the profiling interpreter at instruction boundaries. that helps the compiler quite a lot. And what do we do when we suddenly decide that hey, we have to abort tracing halfway through an instruction? Well, we have a separate, yet another cleanup interpreter that just executes code until the next instruction boundary. And we use that also when we run native code and we fall off our trace path and have to return to interpretation. We can also improve performance by ensuring that we have a representative trace. That means that instead of just finding a loop, we save that trace buffer for a while, and if we come here again, we trace it again, following along in the previously created trace. And then we also allow that trace to fork. And then we, instead of just detecting that we followed this trace along for a number of times, we say that we start generating native code when we have followed it along for a number of, for example, n times, without the trace structure growing anymore, because then we probably found those interesting code paths. And to avoid overflowing, we of course have a limit on the size of this trace structure. We tend to get quite a lot of basic blocks in our traces, and that turns out to be something that really slows down LLVM. We have a large function with a lot of basic blocks. To avoid that, we have implemented trace compression. So it's quite common that we have code looking like the figure on your left, where we have one common basic block at the head of the loop, two alternative execution paths, and a common tail. And as our trace recorder is very stupid, it can create things like this where we have a common tail, but as a pre-processing step before going to native code generation, we detect these common paths and merge them together to reduce the number of basic blocks in the trace. Yes. When we have such a trace, we have enough information to go on to generate code. And that part is probably the one that you'll be most familiar with. Native code generation, we do that by gluing together LLVM IR fragments for the trace. And when we do that, we insert guards to make sure that when we're executing the native code, we stay on the path we have in our trace. And those fragments we glue together, they are extracted from the CFG at the C level, baked into functions, handed off to Clang, compiled to bitcode, and that huge module of fragments is loaded by the jitting runtime at load time. And when we have our trace as IR, we just hand it off to LLVM for optimization in native code. We have one more mode switch left to describe. Or at least two. We have two switches. One switching from the interpreter to native code, and one switching from native code to interpreting mode again. And to switch from interpreting mode to native code, we make use of the liveness information we have in the CFG. So this trace, we package it up as a function where the arguments are the live variables in our interpreter. Likewise, when we're switching back from native code, we have, as I mentioned previously, we have this cleanup interpreter that executes until the next instruction boundary. It is a number of functions, one function for each basic block, which Taylor recursively calls all the remaining basic blocks in the instruction. And when it's done, it packs up all the live variables into structure, which is handed back to the interpreter, which unpacks them and stuffs them into its local variables. To do that efficiently, and as LLVM takes quite a while to do the generation or the code generation and compilation, and this is supposed to be a soft real-time system, we of course run compilation in a separate thread. And also something that is really crucial for getting performance for this is that we need to do a special variant of constant propagation, which is aware of the semantics of Erlang. Because we have the way the virtual machine is constructed, it tends to load quite a lot of data from the code segment, something that's constant. So it loads immediates, it loads register indexes and things like that. And that means that we have a special optimization path that goes through and finds all pointers into our code area and replaces them with constant values as the code area won't change during the lifetime of your program. And that will eliminate loading of many immediates and also of many guards. When we evaluate the performance of our system at the steady state, when everything that is going to be compiled has been compiled, we see that it eliminates most of the instruction decode overhead. We get up to a 50% reduction in runtime on good days. Well-behaved programs around average 25% reduction in runtime. Programs that use cute tricks such as unrolling, something that is good in your in plain interpreter, is not very good when we're jitting, as when we go from bytecode to native code, our code size tend to increase dramatically. And what we see here is more or less cache effects. For the future, we plan full SMP support. We want a special boxing and unboxing aware optimization path, which does constant propagation on those, and that will allow us to remove many useless heap allocations, for example, programs that creates tuples and in the next step disassemble that tuple. We also want to extend this system to work on primitives too. Right now we're just working on the main interpreter loop. Well, that was the Erlang Beam specific part. So now for our experiences with LLVM. First, the strengths. Well, this project wouldn't have been possible without libclang. I don't want to do my own C parsing. I've tried. But you get quite a bit there, but you never are. I know a number of people that has started but never finished on that project. The quality of the generated code is good when we have it, or when it's done, I'd say. And the optimization framework worked very nicely for writing our own optimizations. Weaknesses, on the other hand, is much more on that slide. And I want to say that I'm not saying this to antagonize you. I hope to get suggestions for what I should do differently. The first one is the lack of thread safety in LLVM. We had to do a lot of extra bookkeeping to do things in the correct context. And it is going to be worse when you get to full S&P support. Compilation could be much faster. Right now, we have code that we interpret in maybe around 100 milliseconds, and it takes 5 to 10 seconds to compile it. Also, a drawback is that the native code we produce has to be packaged as a C function, and if we're using MCJIT, even has to be packaged as a module, which makes it quite hard to do things we would like to do. For example, we would like to be able to patch our ready compiled native code, for example, for inserting things when we start tracing and then generating a new execution path that we haven't seen the first time around. So we would really like some way of marking a place in our IR and say that at this point I would like to get access to register assignments and things like that to make it easy for me to patch in another chunk of native code, not necessarily package it as a function. Yes. Also, although we use LLVM for our JITting, we are still compiling our main interpreter loop with GCC. And the main reason for that is due to two things. One is that LLVM doesn't understand to put our virtual machine stack and instruction pointers into registers. They allocate it on the stack, so it's a very many stores and loads from those. Also, it looks like before indirect jumps, LLVM inserts an instruction sequence which is only really needed for a particular or a few targets, but it inserts it before all possible jumps there. GCC apparently makes a better job and just inserts it before the particular target where it's needed, which those two things are combined cost us around 15 to 20% slowdown if we would be using LLVM for main interpreter. If someone is interested in digging into that, I can give you examples afterwards. Although this can sound negative, I want to say that we're very happy with LLVM, as without it we wouldn't be able to get this far with this, I'd say, rather moderate amount of work. So now, that's it. Questions?
Okay, thank you a lot. Any questions?
I'll start.
Hi. A couple of questions. First, what version of LLVM did you do your work with?
3.4.
Okay. There's been a few things, if you go back to your previous slide, because it just makes it easier. The thread safety I'm kind of curious about, but the patching native code, you'll want to take a look at the stack map and the patching code that's been put in since 3.4.
Okay.
I haven't seen you post to the list ever with some of your issues, so
No.
Exactly, and so you probably wouldn't. Posting to the list and communicating with the community about some of the work, if you're not worried about being scooped by other researchers, is probably a better way to get your answers in a timely fashion. Yeah. And as far as the main interpreter, yeah, you should probably file some bugs and just mention it, because other people have direct threaded interpreters and they're not seeing code generation that's this bad. So it could be something specific or it could be something weird, but it'd be best to do that. I wasn't really quite sure what you were doing. Can you elaborate when you fall off trace, though?
Well, as I said, instructions are very SISky, so you have multiple cases. For example, if you're doing addition. Then you're working on small ends, so it's on a 32-bit machine, for example. Then you have 2 tag bits, so you're using 30-bit ints. So typically you start, for example, you're bumping out up a counter, and then you suddenly go over.
No, I'm sorry. I meant what you do when you actually fall, like the cleanup mechanisms that you're using. There wasn't a whole lot.
You need a guard to figure out
right.
that you're falling off this path,
right,
traced and seen, and now you're in
yes,
an unknown.
Yes, I've done all of that before. I was curious how you're calling back into your cleanup code, or how you're exiting from the how you're bundling up the data that you're passing back into your main interpreter loop.
Okay, and the neat thing is if you study the set of live variables inside your interpreter, is that although there are, what did I say, 450 different instructions, there is very little, or not very much state that is valid between those instructions. So I think there are around 17 or so distinct state sets. So
and you just keep track of each of them.
Is I just generate C structures with those fields that are live at those particular points.
Sure.
And then in our cleanup code, we just.
It was what the cleanup code was that I was more interested about, but we can talk later and figure it out. Also, I can tell you how to solve your boxing and unboxing problem too.
Yeah.
So.
That's good. Thank you.
Okay, next question.
Good afternoon. My question is on, you said you had a 25% improvement with well-behaved programs. What was the metric? How did you define that? I didn't really understand that point.
Well-behaved.
Well-behaved. It's 3 or 4 slides behind this one.
The term well-behaved.
Yes. What was the metric for well-behaved?
It's rather fuzzy, but it's programs written straightforwardly, not trying to do cute tricks with knowledge about the interpreter.
Thank you.
Okay, thank you a lot. Next question. Okay, so, one second.
Yeah, hi. You mentioned at one point in your talk, said something along the lines of if you're using MCJIT, you do one thing. So I guess are you using MCJIT or the old JIT, or kind of?
We started out with the old JIT, and now we have switched to MCJIT.
So I guess what were your experiences going from one to the other? Was there any kind of problems there, or?
MCJIT tended to be a lot more picky on what you could give it. And also the switch, we switched to MCJIT in 3.3, and we had to shape up our code generator a bit, and then we switched to 3.4, and then we had to shape it up even more. But at least what we could see is we got a big performance bump in the generated code.
Okay.
You mentioned long compile times. How are you how many basic blocks and instructions per basic block are we looking at in the functions that you're JIT compiling? And how do you have any idea of like the general profile of the kinds of instructions? Is it a weakness in the code generator, or because 1 to 2 seconds is a lot for a function, no matter how big your function is?
Yeah, worst case we have around 1,000 to 2,000 basic blocks in a trace. So I'd say that's a pretty large function.
Pretty large function.
Okay. Any other questions? Okay, I guess it's time for the second speaker. Thank you a lot.